So we have a great set of speakers, and this afternoon we have our first speaker, who is going to talk about Arctic climate change in general, Arctic climate change where reality exceeds expectations. Mark's a good friend of mine. We were cohorts at the University of Colorado 20 years ago, basically a long time. Mark's a well-known expert in many aspects of the Arctic climate system, and I'll just leave the floor to Mark.
Okay, well, thank you, Martin, for that. Arctic climate change, where reality exceeds expectations. Some of you may have been at AGU last December when I talked about this, so what I'm going to present today is similar to that, some updates, some differences, okay, but there's a little bit of a repeat here. I think the place to start, before I do that, if you're wondering what that is in the top left, that's our mascot at University of Colorado. That's Ralphie 4, an American bison. Incidentally, Ralphie 4 is being retired. Ralphie 5 takes over this autumn. Take yourself back 25 years ago. My first introduction to the Arctic on Ellesmere Island near Lake Hazen. I didn't have as much gray back then, clearly, but global change back then, I certainly wasn't thinking of it, bah. In fact, my objective up there in this little ice cap near Lake Hazen was to examine through various measurements of the energy balance the idea of instantaneous glaciarization. This idea that you cooled climate system, get feedbacks going, grow continental ice sheet. Okay? So I certainly wasn't thinking about global change back then, not in the sense that we're talking about it today. Why is the tent upside down? As I recall, it's only because it was the first time in several weeks where the wind was calm enough so that the tent wouldn't blow away so I could dry it out. But in any case, a lot has obviously happened in the past 25 years ago. We're not talking about global cooling. Things are heating up. And the changes in the Arctic have been particularly large. We always kind of knew this would happen. But it turns out that some of these changes are even exceeding what our climate models are projecting. So, in any case, where do we go from here through the 21st century, peering into the future? Well, in terms of climate science, of course, we have to have our crystal ball, and our crystal ball in this sense is our coupled global climate models, such as those used in the recent IPCC report. That's our crystal ball. So what's going to happen? Well, we know that it's going to get warmer, of course. How much warmer in terms of the global average, of course, depends largely on us. What is going to be the path of greenhouse gas emissions through the 21st century? Are the increases in greenhouse gas emissions going to be fairly modest, as in the IPCC B1 scenario, where humans get a little bit smarter, we start to bring on new technologies, things like this, knock down some of those carbon emissions? Do we go on a more business-as-usual approach, the A1B scenario, which is a widely used scenario in these climates? It's probably the most widely used. Or a more aggressive A2 scenario, where it's pretty much gung-ho, let's go and burn the carbon. Okay? Turns out, actually, my understanding is right now we're well beyond the aggressive A2 scenario right now. Okay? Well, let's go with the A1B. All right? This is looking at global temperature changes across the globe, looking at different periods, 2011 to 2030, 2046, 2065, and onwards, compared to a modern-day climatology. And this is the average from a bunch of different models. And as you can see clearly as we go through time, of course, global temperatures rise. The scale here is in the reds, is of course warmer. We're all in the red. It depends, of course, very much on the scenario. Okay? The more aggressive the scenario, of course, the warmer it gets. But the thing you see, where does it warm the most? The Arctic. Arctic amplification, that's the term that's used here. The idea that the change in temperature, the rise in temperatures as we start to load the atmosphere with greenhouse gases and other things, will be most pronounced in the Arctic. Why? Okay, a number of reasons. I think most of you are familiar with these. There's some things like changes in circulation, the strong lower stability of the Arctic atmosphere, but the big one is feedbacks. Okay? The idea is that as we lose that ice cover, it's a self-perpetuating thing. Turns out if you look at this a little more carefully, you find that the big warming in the Arctic is focus number one, Arctic Ocean. That's the big signal, Arctic Ocean. okay, also has a very strong seasonality to it. Autumn. The idea here is you lose that sea ice in the early autumn, like in September, a lot of open water. Now the sun starts to set, okay, things cool down, but now you've got all that open water pumping gads of heat into the atmosphere. Okay. That's really the signal that's going to be emerging, Arctic amplification. Other changes, well, terrestrial changes certainly, warming and thawing of permafrost. This is slide is from a paper that came out a few years ago, read by Dave Lawrence and Drew Slater, rather controversial as I recall in the permafrost community, which was arguing from the A1B scenario that we're going to have a lot of the big loss of what they're calling near-surface permafrost here. I'm going to talk about near-surface permafrost, and this particular run was that in the top 3.5 meters of soil column. So basically the idea is anything in the color here is in this model, which is the CCSM3, where we have permafrost today, essentially. Whereas in the purple here is where you'd expect it in 2080 to 2099, okay? Rather radical loss. This is just looking at it, taking over the northern landmass as a whole, how much of this permafrost we have in millions of square kilometers, going through present day out to 2100. You see this loss. Now clearly you can see how this relates back to the emission scenarios, okay? What's going to be the greenhouse gas loading? Are we going to be on a fairly modest one, like this B1, okay, or something down here? This looks probably to be more likely. If we get that constant commitment, it's never going to happen. It's already passed. The idea there was you're going to commit to 2,000 CO2 levels. Dream on. Didn't happen, obviously. What else is going to happen? Well, we project that the hydrologic cycle in the Arctic is going to accelerate. Basically, you can think of this hydrologic cycle in the Arctic, of course, as that we have precipitation over the oceans and over the land masses. That falls, some of it evaporates up. We have river runoff into the Arctic Ocean, freshwater sources to the Arctic Ocean. Then there have to be sinks from the Arctic Ocean down to lower latitudes via ocean currents. And a paper we had a few years ago tried to put this together. Here's an ocean box, and basically all these arrows are just the fluxes coming into and out of that box. When we think of an amplification of the hydrologic cycle, the best way to think of it simply is that the arrows get bigger. Okay? Certainly you can have changes in storage, like in ocean freshwater storage, or in water storage in the atmosphere. In other words, you increase the absolute humidity. Okay? But the real thing is we're talking about that the arrows are supposed to get bigger. This was simply a run from a number of different climate models trying to illustrate how this works. Okay? But what we expect is, yeah, it's going to accelerate. So why does it precip more? Basically, the atmosphere can hold more water vapor, but there's still a precipitation mechanism, mainly a vapor flux convergence process. Okay? It also evaporates more, but precip wins. Right? This is the basic idea. So what's happened? Well, we know that that Arctic sea ice cover is going darn fast. This is looking at what we had in September of 2007. These lines here are just comparing it with previous periods, the median over a long-term period, of what we had in the previous record, which was 2005. Basically, we lost this big chunk of ice. Last record we had was 2005. 2007 broke the previous record by 23%. It wasn't just that it broke it by a bunch, it just shattered the old record. Here's the September time series, and this one going back to 1952 by combining the satellite observations for the more recent years, starting in 1979, with earlier data. And you can see 2007 really sticking out there. The question is, right, are we getting to a tipping point there? Are we getting to some point of instability where we could quickly lose the remainder of that sea ice cover? And there's a lot of evidence that we may be getting there. Dr. Shrub, in her talk coming up just after me, will look at this in more detail. The interesting thing about this is that this observed loss of sea ice is faster than essentially any of our climate models are telling us it has any right to do. This is looking at the various simulations from IPCC, using observed forcing to the 20th century and the A1B scenario starting in the 21st century. Looking at sea ice extent as a function of time. If you look at these different models, we get to a seasonally ice-free Arctic, or at least almost seasonally ice-free, from 2050, maybe out to 2100, depending on the model. Right? We're obviously well ahead of that. We're probably 30 years ahead of the mean model projections. Thing is, 2008, it's not looking good for this summer. The setup is rather disturbing. Julian, again, will talk about this some more. So again, we would be on this tipping point. Okay, why are things evolving so much faster than we thought, even from the models? A lot of things going on here, okay, which we haven't quite resolved. But the picture here is that we are on the fast track of change. Impacts of this, many, many different impacts. Increased access to the Arctic. Lawson Brigham, of course, is a well-known expert on this and has talked a lot about this. Last year, for example, saw the opening of the Northwest Passage. First time, at least in recorded history that I'm aware of, that this happened. You could take a ship in September right down across the Arctic. I'm not old enough to remember when the Goa went through in 1903. Okay, that was Amundsen's ship. Amundsen, right? Took his hardy crew 2.5 years to pound through the ice-choked channels of the passage. The Manhattan, I was 8 years old back then. There was a strengthened oil tanker tried to pound through to demonstrate the viability of the channel. It made it through, but didn't impress anyone, as I recall, except the people who tried it. Okay? This year, you could have taken a sailing ship through, and the Cloud 9 expedition did, in fact, do that. I think they went this way. I think they went that way. But you could take a sailing ship through. So, you know, we're going to see things like the Northwest Passage opening up more and more frequently. We're going to see increased access to the Arctic in terms of extraction of resources, oil, minerals, starts to raise issues of sovereignty, national defense, okay? Environment. Lots of things are at stake here. But of course, we're talking about impacts on the animals that live there, impacts on polar bears. Already starting to see this in some populations. We'll hear more about this from Tim, I think is coming up, just a bit. Talking more about this is just as one of another example, one of many examples how the impacts of a declining sea ice cover are starting to cascade through the food chain. This Arctic amplification I talked about, well, it's here, I think. We look a little more about this Arctic amplification, this idea that the warming is outsized in the Arctic. Here's a run from CCSM3. This is the NCAR model. This one does really well regarding sea ice, by the way. CCSM3 is probably the best one out there. Okay? This is looking here at the change in temperatures over an Arctic Ocean domain, comparing today against future scenarios, starting like 2000 to 2060. So in other words, looking at anomalies with respect to today's climate. This is looking at by month, January through December. And this is time, 1980 through 2080 here. And the warming is in the orange and the red. And you can see is that you expect that the big warming, okay, is not in summer, okay, but it's in the cold season. Turns out to be especially in autumn. Of course, what's happening there is that you're losing that sea ice through the summer. You have all that open water in autumn. Now that ice starts to grow and cool down, and the water's cooled down, but you pump all this heat into the atmosphere. That's your Arctic amplification signal you're looking for. And you can see it clearly here in the vertical expression. This is from the same model, but now this is looking here at height. So that's 1,000 millibars at the surface, okay? All the way up to 100 millibars, way up there in the atmosphere. And this is looking now from the equator to the North Pole. This is only average. And again, reds are words warm relative to today. So you can see what we have here. Here's, it has high latitude, 70 north of the pole, especially near the surface. That's where it's warming, okay? Because you're losing the sea ice cover. Turns out, as far as I'm aware, it's happening. Okay? Different analyses, different reanalyses, like ERA 40, the NCEP reanalysis, will give somewhat different results here. And there's some controversy here about just what these different data sets are showing. But this one makes sense to me. This is looking at this sort of cross-section like I showed in the model, but based on the NCEP reanalysis, atmospheric model. Okay? Equator to the pole, 1,000 millibars up to 300 in this case, looking at October. This is looking at the past 5 years, 2003 to 2007, compared to climatology. Reds, again, where it's warming. Look at that signal, okay? That surface-based signal, really strong in the high latitudes. Look at it this way. Here's looking at the past 5 years, anomalies again, so we're looking at the past 5 years, 2003 to 2007, compared to a climatology. Here's July, okay, red is warm, right? Not much happening in July. We don't expect much to happen in July because the ice that is still there is melting, basically fixes the temperature to the freezing point, can't budge much. Right? Look at October, wham. Right? Where is that big bullseye? The area where we've lost the most sea ice. Right? So I think that Arctic amplification is starting to emerge. Impacts of that. You start to heat up the Arctic atmosphere. You start to do things like alter patterns of circulation. You start to have a moisture source, alter patterns of precipitation. These are the sorts of things we have to be thinking about as associated with this emerging pattern of Arctic amplification. You might say, well, I don't trust the reanalysis. Okay, so let's go to observations. Here's from the GISS analyses, the NAF analysis, based on data, real data. Okay? This is a Mercator projection, but this is looking at trends in autumn, 1960 to 2007. Red means big positive trend. Well, you might question how they do their data interpolations, things like that, but that, to me, looks like Arctic amplification. Mass balance of Greenland. Another troubling picture emerging here. But of course, the thinking was, not that long ago, that as we start to warm up the climate, the mass balance of Greenland starts to turn negative, and of course that starts to contribute to sea level rise. What's surprising us is that how quickly it's starting to lose mass now. This is just looking at different estimates of the Greenland mass balance through different approaches. And the green here is basically from aircraft altimeter measurements. The red boxes here are from standard mass balance assessments, from the new ISAT laser profiler, and from GRACE, gravimetric data. Right? This is just looking at the observation period over which these were taken. This is kind of a range, gives you a bit of an uncertainty, the vertical part of that, in the boxes. You can see basically all of these data sets are saying, negative mass balance, but it looks like it's growing with time. The most recent GRACE data are showing a rate of mass change of about 250 gigatons per year. Look at the most recent data, it's sticking around that number. Right? Bigger than we thought, and bigger than what they're really talking about in the IPCC, because there are a lot of processes here that really weren't considered or that we're just starting to understand. A number of things at work here. Okay? Number one, we're starting to get more summer melt over the Greenland ice sheet. Now this makes sense. That's a negative contributor, of course, to mass balance, more summer melt. This is just looking at sort of melting anomalies and sort of a degree day approach. This is from some recent work by Marco Tedesco. This is just looking at 2007, which actually in terms of melt intensity set a record above 2,000 meters. Another thing here, this thing called a Zwally effect. This was the idea that as some of the summer meltwater actually creeps down to the base of the ice sheet and actually lubricates it and accelerates the flow towards these big outlet glaciers that empty into the Atlantic Ocean. Right? Thinking was not too long ago that this was a real troublesome thing, and that as climate change takes hold and we get warmer, we're going to have that Zwally effect become stronger and stronger, essentially, and give us this accelerating flow. Well, some of you may be aware there's some recent data, which casts some question on how efficient that is or how important that is. One of the things that we're seeing in these big outlet glaciers, and especially Jakobshavn, which I'm showing here, is that as the calving front of the glacier comes back, the acceleration from the right to the left increases. So we're getting this big acceleration through time as the calving front comes back. Well, what's really happening here, apparently, is that as we calve that front, basically the ability of the glacier to pin itself against the fjord walls becomes less. So there's basically less backstress, so the thing can now accelerate from right to left and just dump more icebergs into the North Atlantic. So the question is, why? Why is it doing that? Why is it melting back? Well, one thing is, let's just get an idea of the sort of velocities of this glacier we're talking about. This is looking at the annual ice velocity at Jakobshavn. This is one of these big outlet glaciers that drains the ice sheet through time, and this is looking at from distance from the 1992 front. Just look out here, if you were out here. In 2006, this thing's moving at 13 kilometers a year. So if you wanted to, you could take a lawn chair with a six-pack out there and stay out there for a day, and you could watch this thing move. It really is a galloping glacier. The thinking is, why is that front coming back? The thinking now has to do with ocean interactions. If the oceans are starting to warm up, and these warmer ocean waters are actually creeping down into the base of the snout, actually to break it up mechanically, melting a number of things. Still don't quite know what's going on here, but these things are somewhat disturbing. And there's another idea of this tipping point idea, could be beginning to get towards some instability in the ice sheet dynamics that results in more rapid decay. Warming permafrost, Okay? Another issue. We know that permafrost is warming, and in some areas it's thawing. This is from some work by Tingjun Zhang and others. This is just showing average temperatures, averaging all these stations in Siberia, soil temperatures from near the surface, minus 0.2 meters, all the way down to about 3 meters down. 1950 through 2000, trying to extend this record. This is just a departure from a present-day climatology. You can see clearly a rather substantial warming trend seen at all levels. Let's look at other areas. Alaska, 4 to 6 degree increases in the 20th century, 2 to 3 degrees in the last 30 years. Siberia, strong warming in Siberia, as I just mentioned. Canadian Arctic, Tibetan Plateau, which some people think of the third pole of the planet. Permafrost temperatures are increasing there as well. Why do we care? Well, there's the obvious things about impacts on infrastructure. You've all seen pictures like this. This is my favorite one here in the thermokarst region in Yakutsk, Russia, where that's probably an old Lada, I think. And there's, I don't know, someone's Toyota Camry, maybe like that. You know, there's these sort of infrastructure. Vladimir Romanovsky has some great pictures of this, remember, that he's been showing around, okay? But the real growing concerns, I think, is things like carbon budget impact. This looming idea out there is that as we start to warm and thaw that permafrost, the critters in the soil, the microbes, become more active, okay? And then that is something that we associate then with carbon released to the atmosphere as CO2, as methane. Okay? There's evidence that some of these changes may be occurring now. Some of these observations of methane release from Arctic lakes. There's Katie Walter burning methane over a thermokarst lake in Siberia. It looks like it would be a lot of fun, but kind of dangerous as well. Someday in my life, I have to go see lakes boiling with methane in the Arctic, but this is just one of these emerging concerns. Now, of course, in terms of tipping points, okay, where are we at? Well, one of the tipping points here probably has to do with this Talik Formation, permafrost regions. The idea, of course, in permafrost, you have an active layer, okay, that thaw layer which grows, of course, to a maximum sometime in the end of summer, and then what happens is you start to freeze from the top as the autumn cold wave comes down. And so, but the thing is, through time, eventually you get to a point where that active layer gets deeper and deeper, but then that autumn freezing wave can't come down and catch up to it. Okay? So basically you end up with that unfrozen layer. Start to end up with that unfrozen layer, well, it has impacts on hydrology. Now things like microbes are more active in the winter. But typically, in general, my understanding of this, and I'm not a permafrost expert at all, so please correct me if I got this wrong, is that when you get Talik Formation, you can often have very rapid degradation of the permafrost. Okay? That's the take-home message here. Okay? There's, of course, things going in opposition. Okay? This idea of shrubification of the Arctic, okay? That we're getting more woody matter. A number of people working on this. This is from a paper led by my colleague Matt Sturm. Probably a few of you have seen these pictures. This is a shot from Chandler, Alaska, 1949. These dark areas are where there's shrub vegetation, little snow there. The next shot is from 2001, same place. It's in color, which is so it's not quite fair, okay, but same time of year is the idea. And so you can see, you know, what has happened over that period. So again, you see, it's go back to that one here, 1949, 2001, this dramatic change of the landscape. Okay? Of course, that's sequestering carbon, you know, an overall net budget approach, I guess. But the question is, at what point in time might the carbon release from thawing and warming permafrost take over and overwhelm this effect? Okay? That could be potentially a big feedback on climate change. Okay? Something that's looming out there in the future, and my understanding is we don't really know when. Right? So, just to conclude on this, even our earliest climate models predicted that the effects of greenhouse gas loading would be seen first in the Arctic, and that's where these effects would be most pronounced, largely due to these feedback effects, which are so strong in the Arctic, albedo feedback, a number of other feedbacks. Even 8 years ago, attribution seemed somewhat uncertain, certainly to my mind. We'd seen these changes emerging, but we know that the Arctic is home to very strong natural variability as well, North Atlantic oscillation, things like this. To me, it wasn't a question of if the system would start to respond to greenhouse gas loading. It was really just a question of, have we seen those changes yet? Wasn't clear to me. Well, I'm convinced now. It seems clear, at least to me, that we are now starting to see this effect of this forced climate change. Number of key changes are exceeding expectations from climate models. Greenland's a good example, right? But the real prime example there is in the sea ice. Could we lose the sea ice cover in summer by the year 2030? I remember about 2 years ago, a year and a half ago, I and a few others, Julie and I believe, were on record saying such a thing, okay, and sounded like a rather radical idea. Well, now all of a sudden we're on the conservative end of this. I don't know how that happened, but there's some people out there saying that we could lose it in 10 years or something. The betting pool right now growing is, does the North Pole melt out this summer? Because it's covered with first-year ice. And I don't remember ever seeing that before. We don't know. We'll see what happens this summer. A lot depends on what the weather patterns are that's set up. But to even be speaking of such a thing, okay, to me is just mind-boggling. Not everything is rapidly changing. Hydrologic cycle, this idea of an acceleration. Okay? Well, we're seeing some hints of that. There's a recent paper that's came out with Nature or Science saying that, yes, there have been increases in precipitation like the models project, but the evidence for that is really not all that convincing to me at that point. So this may be something that we just have to wait for another 20 years or so. And much remains to be understood. This idea of tipping point has emerged as a key issue. I hope that my talk will have at least introduced some of these ideas and set the stage for the talk to follow. Thank you.
Great. Thanks, Mark, for providing a very nice perspective.